Welcome back. We're joined by our next speaker, Dr. Mohammad Rahman from Florida International University. His talk is entitled Controlled Fused Intrusion Detection Systems for Cybersecurity in Unmanned Aerial Vehicles. We've got an exciting talk. Dr. Rahman is an associate professor in the Department of Electrical and Computer Engineering and the School of Computing and Information Sciences at Florida International University. He obtained his Ph.D. in Computing and Information Systems from the University of North Carolina at Charlotte in 2015. Previously, he received his BS and MS in Computer Science and Engineering from Bangladesh University of Engineering and Technology. Dr. Rahman's primary research interests cover a wide area of computer networks and cyber-physical systems. His research focus primarily includes computer and information security, risk analysis, and security hardening, secure and dependable resource allocation, and distributed computing. His research is funded mainly by the National Science Foundation, the Department of Energy, the Department of Defense. He is currently leading multiple grants on CPS security. Dr. Rahman co-authored a book and several book chapters and published over 140 peer-reviewed journals and conference papers. He served on the conference and technical program committees for various IEE and ACM conferences. He served as the TPC co-chair of IEE, IFIP, and NOMS in 2023. Dr. Rahman is currently a senior IEE member, and I'll turn that right over. Thank you.
Thanks, David, for your introduction. Just nice. I already shared my screen. Let me go to the presentation more. So thanks for inviting me to give a talk here. Although it seems that the workshop is more about like healthcare security related things, but my talk is a little bit away from here. My group also do some like healthcare security, but somehow I thought it would be more interesting to talk about the UAVs, and many of these problems are like almost like we can see in the healthcare domain as well. So this problem with this UAV-based security may give us some idea about like a CPS security. So let me start from the next slide. So we will talk here, as you said, the presentation overview. So here, basically, we'll talk about two kinds of UV security work, targeting hardware security and network security. Just to, I want to let you know that I have a flight to California at 4:50. So I may finish a little earlier my presentation, maybe at least 10 minutes earlier, so that it can help me to have enough time to go to the airport. And so I may not cover like some of the slides at the end. So anyway, thanks for bear with me. So what is like a UAV and security specifically? And we have seen a lot of uses of UAV, and it becomes like a toy, more or less. So everybody can buy them, small or big or something. They can play with it, although there are many restrictions in different places. But this becomes very like in our side. So it's not like something like only the researchers or maybe the army people may have it. No, it's now like in the public side. So as you can see, for disaster management, electric power grid inspections, or defense and military, what was from the beginning, and also like precision agriculture, there are many other domains there are use of UAVs. Now, the more critical places we use these drones, the importance of security becomes more critical, especially like a defense and military and any kind of public service like electric power grid, like security. Like if you try to do some surveillance for some critical infrastructure based on the mission, the security of UAVs are very important. So if you see here, we are trying to like show some sorts of like understanding how UAV works. And as we are telling you that we are trying to see like a both kind of security. One is hardware security and it's like a network security. So why these two security is important to keep the main mission ongoing as it is designed. So if you see that there are like three ways on the left hand side figure, I'm not sure whether it maybe I can have this pointer. That might be better looking. Okay, so in the left hand side of the figure, we show like three different ways it can be moved. We call it like a pitch, roll, and ER. So the three different ways it can move to have the like the trajectory according to the designed mission. So now, if you see that this is a particular like a so there are like a four propellers, and two of them goes like a counterclockwise, 2 and 4, and 1 and 3 is counterclockwise. So how they will move forward or go back, move left or right, that basically just moving these propellers in different like um, uh, power. So they might be a little bit slower. One of them might be slower than the other. This is the way they control their moves. If you see here how basically it works, very simple figure. It's the original figure is a little bit like complex. So I just took this part that is enough for this like a discussion. So sensor data will be compared with the desired set point. So there are like a flight controller on the drone, and these will receive the sensor data and it will like compare them with this like expected set points, and based on their like a mission or the trajectory, design trajectory. So now the actuator control will be determined, like how much control we need to do to keep the drone on the path. So actuator outputs will be um, done by this flight controller that will be changed to PWM signal. That is basically the hardware signals that will go towards the, it is like a mixture configuration that has different group of like control groups are involved here. But ultimately it goes to the ESC, that is the controller for these motors. This is a very low level controllers. Most of the time this part is known as power electronics. So PWM, this pulse with modulation, these signals will be sent to this ESC, and based on that, it will move this model. So we call it most of the time the duty cycle. How fast it will move, that depends on the duty cycle. So PWM basically controls this duty cycle. So let's move to our like next slide. So now, what are the vulnerabilities that are possible here? If you can see in the figure, it's like a different group of stuff, especially from the firmware that we see this Pixel, this particular Pixel drone to run this flight controller. This is the flight controller is a firmware, so it must work properly so that it do its job. So there are like a communication or the control commands that comes from the ground controller. We sometimes say like a Q ground control. So this from this ground controller, this data should come like correctly. And also there are like a radio control commands. If there are like a remote control or something, those group of controls should come to this like a UAV properly. So these three places, there's a possibility of attack. So it can be attacked on the firmware level, it can be attacked in the like a network level, that is from the communication between ground controller or just like a remote control. And also there are like a devices that we are saying like within this UAV, those are this in the middle, you see the middle, this is the flight controller, and it like the different sensor data, including the GPS sensor. It is like the receiver that gets the data from this ground controller and radio control commands. And there are like motors. There are a few other sensors as well. But other than that, we have this now this controller for this motor. Yes, we have propellers here. Is a quadcopter, so we have like a 4 motors. So there are many ways that attacks are possible. we are trying to show here, like with this like attackers where this are possible. So let's to see it like a more detail. So if we say like, okay, we have the hardware attacks that it can do the physical tampering. For example, GPS receiver, flight controller, or motors that can be actually compromised. So that can make this UAV crashed. There are side channel attacks. It is more or less like exploiting the design flaws. It is not like a design flaw. It is more like not understanding the possible side channels. So it can be exploited to intercept these operations. So it can be like have some sorts of like side channel is two kind of things is possible here. One is like knowing that how it is happening, what group of stuff are happening there. So get some knowledge, insider knowledge. Maybe this like a knowledge of this like a desired like a mission informations that can be like a revealed, or also like attackers would intercept like a drone GPS like link, and that can understand this like a trajectory path. So mission data or trajectory path both can be like understood from here, especially like this duty cycle or others. There are like a lot of like power like impedance, the properties are there that can be exploited to do these side channel attacks. There are far more attacks that we already talked actually, and there are like a command and control attacks that is intercepting or spoofing the RC command. That means you can give a like a wrong idea about your location. Sensor spoofing, and there can be like duty cycle manipulations through hardware Trojan. There are many attacks are possible. So this is the something that is mostly explored in the literature, that is the sensor spoofing, but the rest of them are very like rarely you can see in the like, literature, specifically for UAV. So I think I can skip this slide. This is more about like just maybe I'm a little fast. So intrinsic and extrinsic security. So intrinsic security, we talk about like a more like onboard security, that is hardware and firmware security. And extrinsic security is more like a sensor or control command that comes from the cloud control. Those level of security we consider here. So now here's like a the architecture of this, the overall like a onboard system, drone onboard system, where you can see that which group of attacks are possible here. There's like a power management and PWM generation board, and where you can actually manipulate this system that can cause like a rapid battery depletion, or you can do like excessive power use, or you can do like reduce the mission duration. As a result, the expected time of like doing achieving the mission that may fail. There are like another kind of attacks are possible, like falsifying the voltage or current data to the PDB. It is more like a false data injection attack, and based on that, you may actually risk like a premature power cut. That means if you say that the battery is very low, you may actually take some like fail-safe controls, and that may actually again the failure of your mission accomplishment. Now you can have like a flight controllers that are most important part here. Basically, if you can compromise this flight controller, this firmware, you are very much like control of the drone itself. This is very like crucial here, and also like a PWM signal that is generated through like by this flight controller, and ultimately there's like a PWM generator. Where you can be like intercepted or disrupted through like hardware attacks, or even can be on the firmware side. The generation of these PWM signals can be like manipulated. So if you can control the PWM signals, you can make like a different group of damages to these drones. Even it can be like the crash of the system. So the EHC is that very low level controllers that control these motors individually. They're based on these PWM signals received from this a flight controller. So it can be also like a tempered, so that the way the PWM signals is like directing, it may follow something else. So in this research, we focus on like a both part, hardware security and network security. I will start with the hardware security in my discussion. And so that I think that might be the most important, like a more nicer part that I can present within my limited time. And firmware security, when we talk about the hardware security, it comes with firmware. Sometimes we call it separately, but somehow we see that it's like in between of network security and hardware security. This firmware can be compromised to do both kind of attacks, maybe at the hardware side, or it can be like a network side, especially with this like a received data, received sensor data, or received control commands that you can manipulate and launch attacks on the drone. So now we'll talk about the hardware security, where the idea is to like PWM manipulations and or build like a hardware trojans that can do the PWM manipulation or something like a more than that. We have papers published, both of them just got accepted. ISQD paper will be presented like a day after tomorrow, and because of that, I'm basically going to California today. And this is about side channel driven information systems for mission critical UAVs. The other one that we recently accepted in Asia CCS, so it is Confide. It is the PWM driven control fused IDS for hardware security. Now I will start with the number one. Okay. So let's talk about the this motivation. Why? And I believe in the beginning I talked about like a duty cycle and something more about PWM. That basically the case how it can be manipulated and how we can actually try to understand this PWM's behavior, and through that we can leverage those information to have a better ideas. So as you said, PWM signals can be manipulated to cause like unauthorized maneuvers or crashes. While the existing security focuses, like as you said, mostly the security research that we have seen for UAV was at the sensor level. So your sensor data might be correct. You have Intrusion system at the sensor level. You check that, you validate that, and you see that it is perfectly good to work with. But at the end, when the flight controller made the decisions, the hardware side, there can be like manipulations. So ultimately, you are in danger. So UAV supply chain, how to say like how this can be attacked. So the one of the simpler attack path is this can happen during the supply chain. And because you know that most of our devices are brought from like outside, especially from China, so there are a lot of like possibilities of such intrusions in our systems, backdoors, hardware trojans, and many other kind of malwares are possible to be placed in the system. So now there are like a hardware trojans, as you said, which can leak sensor data, manipulate controller values, alter paths, can cause the crash. That can be done through the intrusions during the supply chain at the manufacturer side. And there's like an on and off times for PWM regulate the time that we call like a duty cycle. So you can play with this on and off time to control or manipulate the desired control to change the directions of the UAVs, or even fall it down to the ground. So as you say, sensor security does not guarantee end-to-end security. So this is the value we try to put in this work, that we need to do more. So sensors, as you said, the sensor measures this like attitude data, attitude of the drones. That means this all this behavioral data of the drone we find from here. So including this altitude, this like location, and this speed, and many other informations we can get from here, including the battery uses and others. The controller takes actions based on this data. So based on the data, it understands like, okay, according to this current data, it understands its states. From the states and the weight estimates, it knows that what needs to be done to keep the trajectory on the path or keep the main mission running properly. So PWM activates these controls, as I said before. So if we can play with the PWM, the current IDSs act before this PWM generation. That is the point. So if then we can have like attacks at the lower level of the PWM generation level, then we can't detect them, and so we will be in danger. So our attack goal is like it's stealthy alteration of like the idea that we say that attack model we consider here, that this will be like a stealthy alteration of the PWM signals using this hardware Trojan, or maybe like some malware is also like it can be used for it, farmer malware, to lead the UV away from its intended behavior. So when we say like it's stealthy, I will say like if an UAV does not behave as it should be, then that will not be used for like a mission. It can be easily visible that this UAV is not behaving properly, so you will not use that. So most of the time, these hardware Trojans, the way the name says hardware Trojan, they don't get activated always. They get activated like a very like a specific like commands, or maybe very specific like situations. They can be triggered, or maybe they can be triggered for different like situations, but they may not be like for sure not consecutive, very scarcely happening, like those triggers keeps it stealthy. So the attack technique, as you said, like a hardware Trojan based PWM manipulation that we consider here. Here you can see like this like a circuit diagram for this hardware Trojan that we drew here, and you can see that the trigger is activated when specific conditions are met. So you have your like a Trojan trigger circuit that will trigger this like your Trojan payload. So if it is triggered, then your payload will be like executed. And the idea of payload is to like do something like malicious, which can be very serious, which can be like little like a simpler, so that it can remain stable. And but the most important part is this like a trigger part, where you can actually trigger the system very like very scarcely happening, so that it remains like it's healthy. But once it is triggered, but the rest of the part cannot, maybe like a very damaging. It is depends on like the goal of this Trojan payload. So benign, and we will have like a benign and malicious samples that we will like try to like gather, and from there like we will see like how things basically that will be used for our ideas design. Now here we can see like how that is behaving. For we have like a 4 channels here for motors. That's why 4 channels. It is a quadcopter, as you know. So that we basically consider for this particular research. And you can see that the benign samples and attack samples, there is some like a distinction. So these distinctions, if we can learn, we will be able to understand the like we will be able to detect some attacks scenarios. And we will see like how we are successful to doing that. So let's like attack one that we consider here. That was a random alteration of PWM values for the like the models that we did. So if you can see that through this graph, I hope it is visible at your side. So if you see that the like this malicious PWM, benign PWM, they are most of the time they are not actually like a very much distinct. And if you can see that during the malicious PWM signals, it is more like a disturbed, and the signals are more disturbed, as you can see in C and figure C and figure D. So now the second attack was more like a random alteration of the PWM values for the models. But here what happens that we can see two things, that is basically kind of attacks we did, like how we make this like a duty cycle. So we change the duty cycle by 500 units in one case. Another case we did it just like a little more, 525 units. So what's happened, if you can see that in the first case, in the first mission, it was continued, but it was distracted. So it was going at the end towards the end, but maybe we just stopped at some point, so it could go to the end. But in the next one, in the case B, it got like a crash because the alteration was much more than it can tolerate at some point. Yeah. So we have, this is the confide like a framework that if you can see, we have like four modules here. So let me just go over it very quickly. So the first one is like a ground control station, from where you have this data set that comes to you. So it is like a data set formation with data collection and preparation. Next one is this like a PWM mapping. We have two phases here. You can see like a phase, the phase B and phase C. These two are the parts basically where we try to get the information or the pattern, try to realize the PWM information through which we will do our next level, that is the classifications, where we will say that is bad or good. So we try to do the detection in this last module, that is module D. So in the second case, that is in the module B, that we do regression, use the regression for control optimization. And in C, basically, we are doing this like a training. So for the control optimization, it is also like a regression machine learning somewhere. Like in the second part, we are also using like autoencoder based like a training. And these two helps each other, and we will see how the results actually, we see that this both of this idea, how it helps to have a better intuition system. That was the evaluation we did on like a real system, as you can see, how it was connected through the computer. We try to collect the data through this like a breadboard. The breadboard, you see that this is actually the Trojan we built, and then we connected it with this hardware this like a drones. But you can see that since it's like a lab, in the lab we can't have this propeller, so we just remove those propellers to do this analysis. Of course, this data may be a little bit shifted than what we expect, but it was enough different from this the benign data that was properly we could use that to build our ideas. But if it could be like a real a data, then we may find a more better performance, we believe. So these are the channels we have, like a number of channels at attack, then the accuracy, F1 score, all this precision that we can see from here. Matrix with combinations of PWM channels in a UAV attack. So we can attack one channel, we can attack two channels, we can attack three channels, or we can attack four channels. So based on that, we have seen our behavior, how this performance of this confide, how this confide can detect the attacks. So we see that when more channels are attacked, you have especially three channels are attacked, you have more understanding of your security perform better. It is more like a detectable than four. It is very interesting to see why this happens, but I'll talk about it later on. But let's see our result first again. If you see that this figure shows the performance that varies based on the number of attack channels, and as I told you, the behavior is the when it is only one channel attacks, it is hard to detect. But when the more channel attacks, it becomes a more easier to attack them. But we see the same scenario for ROC, AUC score. But as I was telling, when you have 4 channels attached, somehow it is not performing well. The reason is not like very obvious, but what the understanding is that for this particular scenario where we try to use these two phases, one is regression and another one is autoencoder, these attacks some way actually nullify each other. So one of the attacks might be somewhere but get nullified with maybe some other attacks, because we have two pairs of controllers. Two of them goes counterclockwise, another two goes anti-clockwise. So because of that, maybe when we attack all four, the behavior doesn't remains as prominent when we have a 3 channels attack. So anyway, so let's the point is here that we have a more results here. I can skip this part, I believe. Okay. I say confide detect other attacks such as GPS spoofing. That's a very important part here, because we build our ideas to detect the lower level attacks, that is the PWM generation level, hardware Trojan level attack. But we can say that even if the attack happens at the GPS spoofing, that means at the sensor level, still we can do we can detect them. And our performance is really high when the GPS spoofing is at very a large amount. Then it is just completely, it has 100% accuracy. So let's go with maybe I will have another 5 to 7 minutes I'll take for this another hardware security paper we have. It's just a few slides. And so this is the paper that is about the side channel driven information system. So as you can see, hardware Trojans effect that you said is a big challenge, but this doesn't go because you have a change in the circuit. You have an added component in the circuit, so that can be visible through some properties. So those are the properties of basically the side channels. So we developed a side channel based information system here against hardware Trojans, where this group of hardware Trojan can selectively alter the PWM signals or other kind of modification it can do. So the idea is to consider the impedance as a side channel to understand the signature that will differentiate between the benign and malicious cases. If you can see on the right hand side, if you compare the impedance, they are a different. The without hardware Trojan, that is more organized, more pattern than the signal that the impedance a value that you receive when it is with a hardware Trojan. So this is the way we can try to understand this behavior to detect hardware Trojan if it is in the system. So the other one, this is another graph you can see that is from this VNA, that is vector network analyzer, where you can get an impedance, see the behavior of impedance, and you can see that the golden model is the model of the benign case, and you see it is a very natural. But in case of when we have the hardware Trojan, it is very disturbed. So it is very easy to understand the presence of irregularities, and that can help us to understand the presence of hardware Trojans. So this is the hardware Trojan implemented here. This is looks like what has been done. We try to make this trigger as slow as possible, so that we basically our purpose, the initial job was to have this thing trigger in once every 16 times. So every 16 times, only one time in average, it will be a trigger. That was the idea of building this a hardware Trojan. And what we did here, if you say how it works, we have this peak stop that where we implemented our this is our UV. We added it to our a VNA that where we measure the impedance, and then the PWM signal goes to a hardware Trojan that will be like triggered based on this particular combination of PWM signals, and then the payload circuit will be like activated, and where we will try to also know this like a number of times it got like activated. So because we have some like evaluation, so we put a Arduino device to understand, to count these activations. And so this was our like overall like evaluation model. So, if you can see like here's like some 10 minutes time, if we have like a time frame of 10 minutes, if we see that like how many cycles, there was like a 2251 cycle, and we see like a almost like a 3.5 like a percentage of like hardware activation. But the more we keep it like a running, the hardware activation increases. But in average, we saw it like for more than 4% for this like activation. So now the proposed defense, what we do here. So we have the UAV with hardware Trojan. We try to get this data. So DNA data that will collect, that will give us the impedance, that includes the resistance and reactance. And then we will use the trained, we are model based on this like a data. And we use like classification models. And from there, we'll evaluate the classification predictions. As you can see, and we use like a neural network with XGB to detect hardware Trojan. And now we have few like a results here. So if you see like the first graph that shows this like a matrix for different thresholds. So one, we use like a 1 plus SVM just as like a comparison with the XGB. So XGBoost always do like a better. So we know that it would perform better, but naturally 1 plus is also like a popular. So we are trying to see that how both actually we can compare them. And since like XGBoost is like ensemble based like models, it works really well compared to like a 1 plus SVM. So if you see this like a performance, like if you see that 1 plus SVM can go up to like a 60%, where for this like XGBoost it goes like pretty much like almost 100% success. So if you see like this figure like on this like especially on the left hand side in the down figure, the performance versus the varying trigger frequency. Here we are trying to show like, okay, if we increase the trigger of this ACE hardware Trojan, how that will impact. As you said initially, we tried in the beginning to have it like every 16 time in average, it will be like it will trigger, but we increase the trigger time when you make it in one time, it will be trigger, and it goes too low, it is one. And if we can see that the more it's tilted at the very end, we feel like it to like a detect that. But it's still our performance is like 90% if you can say that. So the like overall like our performance ROC is really good, and our like accuracy is very much like more than like a 0.884% when it is a very steep where the attack. Just to let you know that, so when it is very stealthy, when the changes happens really low, specifically here, it is just changing like altering the PWM signals. If it is on, we make it off, or if it is off, we make it on. So just doing this like a 148 time, it doesn't make like a lot of like impact on this like on the mission. So ultimately that is less like impactful. So even if you cannot detect like very high accuracy or very like a high F1 score, but still that is enough to like keep the system like running properly. So I can skip this like a last graph. So I think let's like conclude my lecture. Let me go very end. So maybe 35. So this is my research team. I just wanted to show them because they are the ultimate like people who run my lab, and they are the people who do the most of this stuff. Especially Muniba Asif and Alejandro. These are the two guys. who and this Alvi Ataur Khalid, they did like this work that I have presented today. So, Alvi Ataur Khalid, that paper I couldn't present, but that was in this like presentation. But hopefully, in another time, if I have like find something like another opportunity, I may go over this like other works. Okay, so if you have any question, please. I'm available to take it. I am maybe another 5 minutes. I can be here. Sorry for being like a hosting.
Okay, thank you, Dr. Rahman, for a wonderful talk and uh, pro provide some insights about your research in our workshop. So, is there any question from the audience for Dr. Rahman?
Yeah, hi, I have a question. Dr. Ashique, thank you for your great talk. And really appreciated. We got valuable information related to UAV and cybersecurity. And again, congratulations for your papers accepted in conferences. And I have two questions. First question is how to integrate this UAV concept in healthcare domain. And second question is if we integrate UAV communication with healthcare domain, then what kind of attacks we can expect?
The first one is a little bit easier. I think let me start with that. As I was saying about the hardware Trojan, so it is like a firmware we have on the UAV, this is the flight controller that runs it. So if you can compromise it, so ultimately you can compromise the whole like a device, or some way you can do many steps, including like revealing the information. But all of our, like especially in the smart healthcare, now we have the implanted medical devices. So it is on your like a body, just like a UAV, it is like autonomous kind of stuff. So you have your body, you have it takes the like a data based on it, makes it the decision. Like a pacemaker, it can be like a insulin pump or something like that. That is more like a control by itself, like that we call it like a cyber physical system. So those group of places, if there is no like a outsider validation, no like a third party to validate this data, this hardware Trojan kind of or firmware attack kind of things can be very like a negative impact there can be. And now the question of communication, can you just ask the question again, like Uttam, are you trying to see that whether use of UAV in the healthcare, or trying to see the same kind of communication attacks, whether it is possible in the healthcare?
Yeah, my question is actually UAV can be integrated in healthcare, but why we should integrate, first of all? Obviously, there should be some benefit. And second question is if we integrate UAV in healthcare domain, then I think attack surface, that surface will be big and we need to consider more attacks. And then probably existing tools we can use and we may need to design algorithms or something like that. That is my question.
Yeah, so this part basically, if I say it, if I understand it correctly, so use of UAVs in healthcare is like not basically talked a lot so far.
Yeah.
So, but if you see that it is an autonomous device, am I right? So there are a lot of autonomous device driven like operation surgeries there recently, they're getting popular in case of like a smart healthcare. So if those things are more and more getting like autonomous, that is not yet, then the problems that we can see for UV, similar problems we can easily can see here as well. But if you want to see like a use of UVs for like healthcare, that might be more or less like patient like some medication, this and that you can just like Amazon, the way try to like take goods from one place to another place, like do this like a delivery that can be done here too. And we have like a lot of like robots up there in this like a new different universities now that carry your food. So you order and it comes to your place and you take the food and you eat it. So it can be done through the UVs now. It will be, window, open your window and you have your food. So many things are possible there. So similar things are possible for healthcare might be. I believe even we may not be able to see it very nicely now, maybe a really short time. But if you do some like a brainstorming, we should be able to see a lot of use cases maybe in healthcare too.
Yeah. Thank you.
Sure.
Dr. Rahman, there is another question from the audience, which might be the last question. What are the next steps in UAV research?
Oh, that's maybe like the toughest question we have, because to my understanding, I am very much like the side where it there was few things remaining, and maybe we touched that, and we are kind of doing that part. But I shouldn't say that we are done with what we're doing, but we try to see this like from a like an end-to-end security point of view. Very end-to-end means like from QGram control, from the ground controller up to the like this motor. That's me up. So the whole path needs to be secure. So I showed like at how the Trojans at the like the flight controller and the next level, that is in the PWM generation level. But I didn't show any attack at that little more like a lower level. That is at the ESC that runs this like these models. So those group of attacks are also like a possible very low level. The idea is the same, but now your attack point might be a little bit lower. So we in our project that we are now doing that is supported by NSA. We are going towards the towards the down to the end. So that is in our plan already, and we want to have like a different depth of ideas. So you cannot have a single ideas to do everything like detect everything. Although we showed that the PWM based like these ideas was very good to like detect the sensor data, spoofing attacks and other things as well. But to have like a more accuracy, you may need to have like a different layer of like an intrusion system. Of course, you must consider the feasibility of implementing them, because if you want to implement an intrusion system very low level where the controller is like ESC, electronic the devices, those cannot actually run like a large system, all right? So there are a lot of compromised situations, especially the feasibility that must be like understood very well to see this like how our research can be implemented in the real life. Just give like a quick example, maybe that will be the last thing I want to add here. If you see that we are talking about the last paper that was about the VNA, where that we used to detect this impedance, like we measure the impedance. So we need to have like a very lightweight device that can detect this impedance. So our VNA is like a little bit large. Usually for like a small quadcopter, we can't have that with it. We cannot fly it with it. So there are a lot of like a technological advancement maybe like a needed. So that might be very interesting to see the work to the next level, how our research can be go to like a TRL 5, 6, 7, up to the like the product side.
Okay. Thank you, Dr. Rahman, for your wonderful talk and your insights. And we look forward to like connect with you later on for sure for any collaboration. And thank you again. Yeah.
Thank you all, and thanks for having me here. Bye.